this final discussion of electrochemistry, we're going to relate the potential of the cell to our equilibrium constant and the free energy, and then we'll talk about electrolytic cells, which are more or less the opposite of galvanic cells. In galvanic cells, we use chemical reactions to generate current or to produce electrons. In electrolytic cells, we apply electrons to the cell to force a chemical reaction. So it takes these reactions that would otherwise be non-spontaneous and force them to occur. And this is what's done in electroplating. So we have a few examples of electroplating where we can calculate the amount of material made based on the current and how long we apply that current. So we know that delta G helps us to predict whether or not a reaction is spontaneous. If delta G is negative, then our reaction is going to be spontaneous. We also can relate delta G to E naught of our cell. Delta G is equal to negative N, which is our number of electrons, times Faraday's constant, times that potential of the cell. So if delta G is negative for spontaneous reactions, that means that our potential must be positive in order for a reaction to be spontaneous. The only way that we'll produce current when we're looking at a galvanic cell is if this potential is positive. From the last chapter, we saw that the free energy could also be related to our equilibrium constant, K. That relationship was the free energy was equal to negative RT times the natural log of K. Here, we knew that for this reaction to be spontaneous, our K value had to be much, much larger than 1. In other words, it needed to favor product. If it favored product, the reaction would move forward in the spontaneously, and Now what we can do is we can take these two equations and set them equal to one another. So we have delta G equals negative NF E naught of our cell, and delta G equals negative RT ln of K, which means that negative RT ln of K is going to be equal to negative NF E cell. Rearranging this expression, we can arrive at an equation where we're relating E naught of our cell to our equilibrium constant. You can go through this manipulation if you like. You would simply divide by NF, negative NF on both sides. The negatives would cancel. You would end up with RT over NF, which we can simplify to 0.0269 over N times the natural log of K, and then we can convert that to a log-based scale by multiplying by 2 point something, 2.5 I believe. At any rate, what you end up with is you end up with 0.0592 over N times the log of K. So now what we can do is if we're given a K value for a reaction, we can calculate the potential for that reaction. So here we have, or vice versa. So in this case, what we have is we have the potential. We can calculate that from our standard reduction potentials table for this reaction here, where we have solid iron reacting with acid to dissolve that solid iron and produce iron in the 3+ oxidation state, and at the same time produce an hydrogen gas. For this reaction to occur, it must be that the iron donates electrons to become iron 3+, and it has to donate 3 electrons in that process. Since we have 2 iron, that means that we're going to have a total of 6 electrons for 1 turn of this reaction. The reduction potential for this reaction is negative 0.04 volts. Notice, though, that in this case, the iron is not being reduced, it's being oxidized. So we need to change the sign of our standard reduction potential. The other half reaction that's occurring is hydrogen, accepting electrons in order to produce hydrogen gas. So here, hydrogen is being reduced. We wouldn't need to change our reduction potential. It's still 0. And we would also see that we require a total of 6 electrons for the balanced reaction that's given above. So now what we can do is we know our N value. We calculated E of our cell, so we should be able to find the equilibrium constant using this expression here. E naught of our cell is going to be equal to 0 minus negative 0.004, which gives us 0.04 volts for E naught of our cell. That's going to be equal to 0.0592 over N, and we determined that N is equal to 6 electrons for this reaction here, times the log of K. If I take 0.0592 and divide it by 6, I get 0.0986, and then if I take 0.04 and divide it by 0.0986, I get 4.054. And that's going to be equal to the log of K. The inverse function of log is taking 10 and raising it to that power. So then we rearrange and we find that K is going to be equal to 11.325. So I always like to do a conceptual check to make sure that this makes sense. On the previous slide, we said that for the reaction to be spontaneous in the forward direction, it needed to have a positive E naught of our cell, which we do, and then K needed to be bigger than 1, which it is. So now give this a try on your own. We have an electrochemical reaction, and it transfers 2 electrons. So we're not told which reaction, but we are told what our N value is. And then this reaction has an equilibrium constant of 1.68 times 10 to the 4th. We want to calculate E naught of our cell. And we're going to do that using this equation here. So this is really just a plug and chug. We're going to put 6 in for N. We're going to put 1.68 times 10 to the 4th for K. The log of 1.68 times 10 to the minus 4th is 4.255. And 0.0592 divided by 6 is 0.296. And so E naught of our cell is going to be equal to 0.125 volts. Electrolysis is when we apply a current to our cell. So when we have a spontaneous reaction, we call that a galvanic cell. In an electrolytic cell, we're going to do the opposite. So rather than using a chemical change to generate electricity, we're going to use electricity to create a chemical change. So we can force reduction to occur. We see electrolysis both in refining metals and recharging batteries. So typically we use batteries to supply current. Now what we can do is we can recharge those batteries by applying a current to the battery. So we're forcing those electrons to go in the opposite direction as we apply that energy. Here we have an electrolytic cell, and this is the zinc-copper electrolytic cell. We looked at this example with the galvanic cell when we started, and what we found was that in the galvanic cell situation, the copper was accepting those electrons and being reduced to solid copper. The zinc was being oxidized and giving up its electrons so that it could reduce the copper. And we knew that that was the direction of the spontaneous reaction based on the reduction potentials. So zinc had the more positive reduction potential, and so zinc had the more negative reduction potential and it would give up its electrons. Copper had the more positive reduction potential and would accept those electrons. Now what we've done though is we've connected a battery to this cell. When we connect a battery to this cell, one that has a potential greater than the potential generated when we had the galvanic cell, we can force the electrons to go in the other direction. So now we're stealing electrons from the copper, the solid copper, oxidizing that solid copper to give us copper 2+, and those electrons are going to the zinc, and the zinc ion then is accepting those electrons and being reduced down to solid zinc. So now what we see is the reverse reaction, and we're going to still label our anode and cathode. The cathode is still going to be where reduction occurs, and the anode is still going to be where oxidation occurs. But now if you notice, the anode is going to be at the positive end. Our salt bridge, we're going to see that K plus flows and then our reduction occurs at the cathode, so the cathode is going to be associated with the negative terminal of our battery. So it's non-spontaneous as it's written. We can force it to be spontaneous by applying electrical energy. If we know for how long we apply the electrical energy and the current at which we apply it, we can calculate how much material is going to get deposited. First, though, we need to figure out the total number of electrons. To figure out the total number of electrons, we would use the charge and Faraday's constant. The charge can be determined by multiplying the applied current times the time that you apply that current. And just as a reminder, amp, the unit amp, is also equal to coulombs per second. Once we know our charge, we can take the charge and Faraday's constant, which is the charge for 1 mole of electrons, and convert to how many moles of electrons get applied. Then, once we know our number of electrons, we can use our half-cell reaction to relate the number of electrons to the number of metal atoms that get reduced. So let's do an example of this. If we have a solution of copper and we subject it to 2.4 amps of current for 30 minutes, what is the mass of copper that we create? Firstly, we're going to calculate the total charge that's applied, and we can do that using the fact that charge is current times time. In this case, our current is 2.4 amps, which I'm going to write as coulombs per second so I can see my units cancel, and the time is 30 minutes. However, because I have it in coulombs per second, I need that 30 minutes to be in seconds. So I'm going to take my 30 minutes and multiply it by 60 seconds per minute. That's going to give me 1,800 seconds. Which brings me to 4,320 coulombs. So now I know the total charge that was applied, and I can relate this to the number of electrons. So I'm going to take that 4,320 coulombs, and I know that for 1 mole of electrons, I would have a total charge of 96,485 coulombs, and that's going to give me 0.0448 moles of electrons. That's how many electrons I've added into my solution. For this reaction, I know that the copper 2 plus, when it accepts electrons, it gets reduced to solid copper, and I'm going to require 2 electrons for every 1 copper atom. So for my 0.0448 moles of electrons, we'll require 2 moles of electrons. So that's going to convert, dividing by 2, will convert this from moles of electrons to moles of copper. And then I can multiply that by the molecular weight of copper, which is 63.55 grams per mole. And I arrive at my answer, which is 1.42 grams of copper. So now give this a try on your own. How long are we going to have to apply a current of 50 amps to produce 3 moles of copper? Remember again that the copper, as it's reduced, it's going to use 2 electrons, 2 moles of electrons, to reduce 1 mole of copper. Also remember that your charge which it will be determined, which you can use to determine your number of electrons, is equal to the current times the time. The current is given to us as 50 amps, which is 50 coulombs per second. So our time is going to be equal to the current divided by the charge. So I have to figure out what my charge is. The charge can be determined from our moles of copper. First, though, you need to take your moles of copper and convert them to moles of electrons, and then you can use Faraday's constant to figure out your charge. So give this a try to see what you come up with. So you should see that you're going to require 6 moles of electrons to oxidize 3 moles of copper, or reduce 3 moles of copper to generate that 3 moles of solid copper. So now I'm going to take my 2 moles of electron, multiply that by 96,485 coulombs per mole to arrive at 578,000 So we see that it requires 6 moles of electrons to create our 3 moles of solid copper. So what I'm going to do is I'm going to take that 6 moles of electrons and multiply it by Faraday's constant in order to figure out the number of coulombs applied. And we get 578,910 coulombs. So now I can take my current, my 50 amps, which is coulombs per second, divide it by the coulombs that I need. And I get that the time required So now I can take the current that I've calculated, 578,910, divide that by my charge. Oh my goodness, I just made so many mistakes. It's just so stupid. Now try on your own. So you have a constant current of 50 amps, which again, an amp is a coulomb per second. That's applied to a copper solution, and we want to produce 3 moles of copper. So from my half reaction, I know that the copper 2+ has to react with 2 electrons in order to form solid copper. So I know for every 3 moles of copper, I'm going to need 6 moles of electrons. So 2 electrons for 1 mole of copper, 2 moles of electrons for 2 moles of copper gets me my 6 moles of electrons. And then I can figure out my time because I know that the charge is equal to the current times time. And so time is going to be equal to charge divided by current. My current I know already, it's 50 amps. And the charge I can calculate from my 6 moles of electrons. When you do this, you should get that your 6 moles of electrons are going to produce 500,078 or 578,910 coulombs. So the time will be equal to 578,910 coulombs divided by 50 amps, which is a coulomb per second, and we get 11,578 seconds. I want my answer to be in hours, so what I need to do is I need to take those seconds, divide it by 60 seconds per minute, divide it by 60 minutes per hour. And what I calculate then is 3.216 hours, or 3.22 hours. Let's finish with one more clicker, a little bit easier. So now we have the electrolysis of aluminum chloride. Remember that aluminum chloride, when it dissolves, I'll get aluminum ions and chlorine ions. The chlorine ions have a -3 charge, which means my aluminum is going to have a 3+ charge. For that aluminum 3+, to be reduced to solid aluminum, it's going to have to accept 3 electrons. So for 3 moles of electrons, I get 1 mole of aluminum. And I want to know how much aluminum I produce if I apply a current of 15 amps for 2.5 hours. So again, you'll want to use that charge is equal to time times the current. Once you know your charge, then you can use the fact that you produce 96,485 coulombs. Charge is going to be in coulombs for 1 mole of electron, to convert from your charge to your electrons. Again, make sure that your units cancel. And you'll also have to, like I've already shown, convert this 2.5 hours to seconds. So now that we have the seconds, we can plug in here, and our current is 15 amps. We would take that 15 amps, multiply it by 9,000 seconds to figure out the total number of coulombs applied. This 135,000 coulombs came from our electrons. 1 mole of electrons would produce 96,500 coulombs, roughly. And so that means that we applied 1.4 moles of electrons to our solution. And again, 3 moles of electrons will produce 1 aluminum. So if we have 1.4 moles of electrons, we would produce 0.466 moles of aluminum. That 0.466 moles of aluminum times the molecular weight of aluminum, which is 26.982, will give us 12.58 grams. So from this recording, you should be able to look at either free energy or your K value, your equilibrium constant, to figure out your reduction, the sign of your reduction, the sign of your potential on your cell, so the voltage of your cell. Or if you knew the voltage of your cell, you would be able to say whether the reaction is product favored or reactant favored. Then we have the mathematical side of that, the quantitative side of it, where you can calculate E naught of your cell from either delta G or an equilibrium constant K. So we have that triad where we have the three equations relating all three of these variables. We also went through electrolytic cells and how electrolytic cells are the opposite of galvanic cells, and you can generate metal by applying electrons. If you know for how long and at what amperage you apply those electrons, then you can figure out the amount of material that you would create.